This is Calvin Ho, homework 3A. So here we got problem 1. This is the one of the bucket full of ore, and we want to find the maximum horizontal distance when the bucket swings. So we draw our free body diagram for state 1, then state 2 once it stops, and there's a swing, and we're trying to find this distance here. Yeah. So our kinetic energy at 1 we know is just moving, so we just have our standard 1/2 mass times velocity squared. For the kinetic energy of 2, we know it has to be equal 0 because we're looking for the max height. So we're looking to when all this kinetic energy it swings up and it turns into potential energy, and that's shown here. That the change in energy is just this potential, this change of h. So we plug that into our T1 plus the change in energy equals T2 right there. And we're able to solve for H, which is this 1.55 feet. Then with that, we know this one side and we know this side because this is just that 30 minus that H that we just found. And we have to find D, so we do a Pythag on it. So this side squared plus this guy squared has to equal this squared. And from that, we solve for D, and D equals 9.53 feet. Okay, problem 2. We have this trailer slash truck going up a hill at a 2% upgrade, and we want to find A, the average force at the wheels of the cab, and B, the average force in the coupling between the cab and the trailer. Yeah. So a couple things that were given. The velocity initial is at 72, which is 20 meters per second. Velocity at the top of the hill is at 30. We just have this start point as our x naught, which is 0, and we know it moves 300 meters. And we're also given the mass of the cab and the mass of the trailer. So A, the average force at the wheels of the cab. So we know at our x naught that the kinetic energy is just the standard 0.5. The total mass, velocity initial squared. Then our finishing, which this should be 2, is the same equation, just with our second velocity. And the change in energy is the force, the force at the wheels times the distance minus what is it? H G and the total mass, and that's just the change in potential energy right here, because it's moving up. So some of that energy is converted into potential energy. We plug that into our equation right here. Just our standard T1 plus change in energy equals T2. And then from that, we find that the force at the wheels is 7413.3 newtons. So for B, we want to find the average force in the couplings. It's pretty similar to what we did in part A. But instead, for our equations, we just use the mass of the trailer. Yeah, the trailer, and we're trying to find the force between them. So we have the trailer. We use the kinetic equation, but just for the trailer. Same thing with T2 kinetic equation, just for the trailer. The change in potential is that same F. So the force between the couplings times 300 minus the change in potential energy for the trailer. We plug it into our T1 plus change in energy equals T2 equation, and we find that the force between the trailers is 5559.5 newtons. All right, problem 3. This one's the one of the subway train. We're given the initial velocity is 30 miles per hour, which correlates to 44 feet per second. We're given the coefficient of friction in this first cart is 0.35. Part A, the distance required to bring the train to a stop. So we know our initial kinetic energy is our 1/2 mass times velocity squared. The final kinetic energy is when it comes to a stop, so it's 0. And the change in it is just the work being done is just the work done by friction, which is our friction coefficient by the normal first times the distance. So we throw it into our equation, and then we plug in all our values. We convert these tons to kips. So like 40 tons is 80 kips, 50 tons is 100 kips, 40 tons is also 80 kips for that third cart. So we throw that in, divided by the force of gravity, which is 32.2, into our kinetic equation, and then we're subtracting the work being done by friction. Equals 0, and you find the distance needed is 279.14 feet. Part B, we're asked to find the force in each coupling. So from A to B, we have our kinetic as just the mass of cart A. Our final kinetic energy is still 0, and the work being done is both the work being done by friction as well as the force that this cart A puts on the rest of the carts times the distance. We plug in our values, and we find that force that A puts on the rest of the carts is 19.38 kips. Negative 19.38 kips, but that equals 19.38 kips in compression. We do the similar thing for the coupling at B to C. We're doing it for cart C, as here for our kinetic energy, same equation. The final is still 0. The work being done is that force that C puts on the rest of the carts times the distance. Plug it into our equation, and we find that that force is negative 8.61 kips, which correlates to 8.61 kips of compression. All right, problem 4. So this one, we're given a sphere at point A, and we have to find the downward, and we're given the downward velocity, and then we want to find the angle theta at which the boat will break, knowing that it can withstand a max tension equal to twice that of the weight of the sphere. Okay. So here are given the initial velocity 5 meters per second, the length is 2 meters, and the max tension is 2 times the weight of the sphere. So we do our initial free body diagram, the initial point, and then this theoretical position at theta where the rope would break. We know our initial kinetic energy is just our 1/2 meters times velocity squared, 1/2 mass times velocity squared. The second kinetic energy, the same thing, just at this second point. And then the work done, we know, is the force of gravity times the 2 meters sine theta, which is this distance here. So it's our 2 meters times that sine of theta. Throw it into our equation, and we solve it for velocity squared equals this right here. Then we use our Newton's second law, and we find that the forces here have to be equal to the acceleration forces here. We just have our x and y in those directions. So we sum the forces for x. This is that 2mg minus mg sine theta equals mass times the acceleration in the normal. And then we solve it, same for the velocity squared. We set these two equal to each other. And then we solve it for theta, which we find is 14 degrees. Alright, question 5. This is the ski lift. We know it's designed to transport 1,000 skiers per hour from point A to B. We know the average mass of the skier is 70 kilograms, and the average velocity is 75 meters per minute. Part A, we're asked to determine the average power, and we know power is work over time, so we calculate the work. Gravity times the mass of 1,000 skiers times that 300 meters up over 3,600 seconds, and we're given that power average is 57.2 kilowatts. Part B, the required capacity of the motor if the efficiency is 85% and if we're allowed a 300% overload. So we calculate this overload change. We just add it to 100 divided by 100 times the energy we need. We're given 229 kilowatts. The motor capacity is just what we need over the efficiency, and we have 269 kilowatts is what's required. Alright, here we have problem 6. It's the one where we're given the collar and we know it moves around this loop, frictionless loop, and we have the spring. We're asked to find the velocity as it passes through both B and C. So we're given the mass of the collar, which is 2 kilograms, the K constant, and we know it starts from rest at A. So we're just basically going to start by finding the elongation at both B and A because we know it's not elongated at C. So we're just going to take, so for A, for example, we're taking this distance here minus by the resting distance. We get 0.1 meters. Do the same thing for B. We get 0.05 meters. Okay, then we calculate the potential energy of the spring at A. We know that the equation for potential energy of a spring is 1/2 K times the elongation squared. Given that here, 3 joules. Then we're calculating the same thing at B. Use the same equation. We get 0.75 joules. And we know at C is not elongated at all, so it's 0. Here, we're going to calculate the potential energy due to gravity. We're having this right here be our base point. So from right there, it's 0. So we know that the potential energy due to gravity at A is 0 and C is 0 because it's at this very limit. So we calculated at B, negative mass of the collar times gravity times the distance right here. And then we get negative 3.924 joules. Then we know at A is released from rest, so the kinetic energy at A is 0. Then we calculate the kinetic energy at B and C just with the standard equation, 1/2 mass times velocity squared. So the velocity at B, the velocity at C squared. So A, we're looking to find the velocity at B when it passes through. So we set up our potential kinetic and potential energy at A has to be equal to the kinetic and potential energy at B. So we set our equations and solve for this VB, and we get 2.48 meters per second to the left. Do a similar thing for B, where we're asked to find the velocity at C. This kinetic plus potential at A equals kinetic plus potential at C. Plug in the values that we have, and we know the velocity has to be 1.73 meters per second going upward. Okay, problem 7. We're given this box sliding down, and we're going to stop it with the spring, and we're given some values, and we're asked to find the maximum additional deformation of the spring to bring the package to rest. So we're given the mass of the package, the K constant, the initial velocity here at the distance 8 meters, and then it's initially compressed by 0.05 meters. Alright. So we calculate our kinetic energy here just with our 1/2 mass times velocity squared. We get 100 joules. And we know the kinetic energy at point 2, where the box is at rest, is 0. Potential energy due to gravity at this point A. We take our 8 sine 20 to correlate here. 8 sine 20 times mass times gravity, and we get this right here. To find it at B, we do a similar thing, except we don't know the initial distance it goes down. That's why it's negative, because the potential is going to go lower as this compresses. So we put in this x, and we just use a placeholder right here, times x. So the distance we're looking to find. Okay. Potential energy due to the spring at A. We just plug it into our 1/2 K times the elongation squared. Get this right here. And then we do the same thing for B, except we're going to add this initial distance is compressed. And we get that equation. We do our kinetic energy plus the potential energy at A or point 1 has to be equal to the kinetic and potential at point 2 or B. So we throw in our values, and then we solve for x, and we find that the initial elongation is 0.269 meters. Alright, problem 8. We have this truck going up this incline. We're given the initial velocity is 108 feet per second, and after 6 seconds it reduces to 36 feet per second. We're asked to determine the magnitude of the braking force. We know it's a 10-ton truck, which correlates to 20,000 pounds. We divide that by gravity, and we get this mass right here. So for part A, we know it has momentum. The beginning momentum, is the mass times the initial velocity minus the impulse equals this mass times the velocity at the end. So with this equation, we can plug in what we know for the impulse, which is the braking force, plus this gravitational force at the incline times time. Plug in the values that we know. We know at 6 seconds, so where 6 come from, the velocity is 36 feet. So we use that to find the braking force, which is this right here. Part B, we're asked to find the additional time required to stop the truck. So for this, we use the same equation as above, except we have it equal to 0 for stopping. We plug in the values that we know, the force of braking we just found, and then we solve for t, which is 9 seconds, but we want the additional time. So we take that 9 seconds and subtract the 6 seconds we already had in, and we find an additional 3 seconds to brake. Okay, question 9. We have the system at rest. Then we have a 150 Newton force applied to collar B, and we're asked to find the time in which the velocity of collar B will reach 2.5 meters per second towards the left. So from inspection, we see that this distance XA is equivalent to 2 is YB. So using that, we integrate it and find that the velocity A equals 2 velocity B. We set up our momentum impulse equations. So momentum of block B, the momentum of block A. Then with block B, we're able to set up this equation here, where this 150 newtons times T minus this 2T times T has to be equal to this momentum right here. Using that, and then the equation we find for block A, doing the same thing we found, we're able to solve part A. We just subtract the equations from each other to cancel out these tension T's. We get this right here after subtracting them out, and then we solve it for T, and we find that the time is 0.55 seconds. For B, we're asked to find the corresponding tension in the cable. So we take this T we found, and we can just plug into either of the equations. I did the one for block B, then we just solve for this tension T, and we find is 56.8 newtons. Okay. So next question. This was the one of the bullet hitting the block. We're asked to find the initial speed of the bullet. So we know this length is 2.2 meters, and we know this theta, max theta, is 60. So we set up our momentum impulse for the x direction. We know the blocks. It starts from S of 0. The bullet is the mass of the bullet times the velocity of the bullet. We have these forces, the one acting on the bullet and the bullet acting on the block, and has to equal the velocity times the mass of the block and the bullet together. Then we can use our our T1, which is the initial kinetic energy of the block and the bullet together. We know it's 0.5 times the mass of the block and bullet times the velocity here squared. We know that at T2, once it's at the top of the swing, the kinetic energy is 0. The potential energy of 1 at this position 1, given that this is our initial point, would just be negative 2.2 times the mass times the force of gravity. Then we do the same thing for this point B, which is this right here. The mass, gravity, and the 2.2 times cosine at that max theta of 60. Then we know that the kinetic energy at point 1 plus the potential at point 1 has to equal the kinetic at point 2 and the potential at point 2. We can solve this to find the velocity 1 here, and with that, we're able to find plug that in to our equation from this momentum impulse graph, where we know that the mass of b times the velocity of the bullet has to equal this v underscore, this velocity 1 here times the mass of the bullet and the wood block. We solve that for the initial, and we find it's 778.9 meters per second. Part B, we're asked to find the impulse. We just find this using the momentum impulse graph of just the block. Now the block starts from rest. We have this impulse factor, and it has to be equal to the mass of the block times this velocity. Then we just solve it, and we find that it equals 4.646 joules. Then part C, the force on the cord immediately after the impact. So we have this tension of the cord, weight of the block and the bullet together has to equal the acceleration that the block feels inward right after it is hit. So we set those equal to each other. So this is that tension minus the weight of the bullet and the block times gravity, and then the mass of the bullet and the block. We use the relationship that acceleration is just velocity squared over r. Solve it for T for tension, and we get it equal to 19.74 newtons. Alright, for this next problem, we're given these 3 hanging balls, and then we have, we basically lift A, we give it a sort of initial velocity, and we have it hit the rest. So for part A, we're asked to find the equations for velocities of A and B immediately after the first collision. There we go. So we know VA has this initial velocity, and VB and VC equals 0 for this beginning. First we start with our conservation equation. MVA plus MVB has to equal MVA plus MVB, and that's MVA after hit, MVB after hit. We plug in the values that we know, and we find that V naught equals VA after hit plus VB after hit. We use our equation for E, which is E VB, this should be VA. VA minus VB equals VB after hit minus VA after hit. We solve that, and we find that E V naught equals VB after hit, VA after hit. By solving for either VB after hit or VA after hit, we can plug into our first equation and solve, and then we find that VA after hit equals the initial velocity divided by 2 times 1 minus E, and then VB after hit equals the initial velocity divided by 2 times 1 plus E. So for part B, we're doing the same thing, but instead of A and B, we're doing it with B and C. So we use our same conservation equation. We plug in the values that we know, including this VB after hit right here that we just found. And then we find from that is that V naught divided by 2, 1 plus E that we found equals VB after the 2 hits plus VC after hit. We use our E equation like before, and we solve it. And in the same way, we can either solve for VC after hit or VB after 2 hits, and then solve the equations. So in this instance, we get VB after 2 hits equals the initial velocity divided by 4 times 1 minus E to the power 2, and this VC after 1 hit equals V naught divided by 4, 1 plus E to the power 2. So for this last problem, we're given a block, has an initial velocity of 2, and it's hit the sphere given a friction coefficient and then a value for E. We're asked A to find the maximum height of H reached by the sphere. So we're going to start just with a quick diagram. We know that the sphere starts from rest, and the block has initial velocity of 2 meters per second. And after they hit, we get our VA after hit, VB after hit for the blocks. So we use our conservation equation. We find that by plugging in the values that we know, 4 equals VA after hit plus 2 VB after hit. We use our equation for E, plug in the E that we know, and then we find that the VB after hit minus VA after hit equals negative 1.6. By solving this for either VA or VB, we're able to plug it into this first equation. And then by doing that, we find that VA after hit equals 2.4 meters per second, and VB after hit equals 0.8 meters per second. So to solve the rest of the A for the height, we know that the kinetic energy after the hit that this ball feels is the 1/2 mass times that 2.4 squared. We know that at the max, then the kinetic energy is 0. We have the initial potential energy at point 1 equals 0, and then potential energy at point 2, that max, is going to be h, so the max height times gravity times 0.5. We plug that into our equation, conservation equation. Kinetic energy at 1 plus potential at 1 has to equal kinetic energy at 2 and potential at 2. Plug in those that we just found, solve for h, and we find that h is 2.94 meters. For B, we're asked to find the distance x traveled by the block. We do this kind of in a similar fashion. We know that the kinetic energy of the block after the hit is 1/2 mass of the block times that 0.8 that we found earlier squared. At the max distance, the kinetic energy is going to be 0, and then we know that the work done is the work done by friction that's taken away energy from the system, and we know that friction is the normal force times the friction coefficient. However, since the normal force and the force of gravity are equal in this sense, because it's not going up or down, then we know it must equal this force of gravity. So we can just do our friction coefficient times gravity times the mass of our block times the distance for that force. Plugging it into our kinetic energy plus work equals kinetic energy 2, and solving for x, we find that x equals 0.054 meters.